Mechanical engineering is a very broad major that can be broken up into different subfields or concentrations. Schools will differ by how they label them, but the most common ones are mechatronics, HVAC, and manufacturing. There are many others, but some schools just call all of them the general concentration, and many actually split them up into specific named concentrations like automotive, dynamics and controls, mechanics of materials, thermal and fluids, aerospace applications, and more. I'm going to explain these three in this video, and then in the next I will more or less generalize the other concentrations and group them together to save time. So how I categorize them may not be exactly how your university will do it. So let's first start with mechatronics. First, I want to say that when it comes to undergrad, mechatronics is its own major at some colleges, and most of those seem to be outside of the United States. In fact, when I went on forums discussing mechatronics, almost everyone there was going to school somewhere outside the US. Many people who said they do work in mechatronics in the United States said they are just mechanical engineers that specialized in mechatronics or controls or something similar. So I'm just referring to mechatronics as a concentration or subdiscipline of mechanical engineering. Now, mechatronics is the combination of mechanical engineering, electrical engineering, computer engineering, and even controls. It's very close to robotics. The words are vague in how they are defined, but many people say that robotics is a subset of mechatronics. But when you hear robotics, don't just think of the typical kind of robots you probably envision. It includes self-driving cars with their sensing and control systems, unmanned aircrafts, automated medical equipment, manufacturing machines and processes, and much more. Lots of engineers work on these, but when you hear of robotics or mechatronics, just realize how much this encompasses. In college, all mechanical engineers take a basic circuits class and basic electronics class, but you really apply those the most and dive further into electrical and computer engineering topics by going into mechatronics. Those classes involve a lot of circuits, electronics, and programming. I've said before that a lot of mechanical engineers I've talked to did not like their circuits classes, but many who really enjoyed them went into mechatronics. So an example of a project you can make in mechatronics may include making an analog to digital converter, or ADC. This is a system that takes in an analog voltage, like maybe a sound signal from a microphone, and changes it into a digital signal, or ones and zeros, which if you've seen some of the other videos you know are high and low voltages. And as the analog signal changes over time, then this digital output keeps changing as well, and you get a stream of ones and zeros. So you'll learn about this technique and the circuits that make it happen. This is used in digital cameras, sound systems, some radar systems, and much more. Electrical and computer engineers would make this as well in their embedded systems class, but mechatronics is where there's overlap with those two majors. You can maybe do a lab to make an electronic scale, or one that makes an automated electric motor. There's a lot you can see, but realize how it's not really thermodynamics, fluids, and structures like a mechanical engineering class, but more of the microprocessor design and signals and circuits like an electrical or computer engineering class. Mechatronics engineers are concerned with structures, static and dynamic systems, and so on, just like other mechanical engineers. But they also deal a lot with sensors to detect sound, stress, pressure, temperature, and more depending on the system. Then they also learn more about electrical components like resistors, capacitors, inductors, transistors, and even signals. So if we look at some senior projects, there was one where people made a robotic hand that could form sign language letters based on keyboard inputs to help communicate with those who are deaf and blind. There was one with an automated motorcycle headlight that would physically turn based on the turning of the motorcycle, or even where the driver is looking in order to maximize safety. So if they are taking a sharp turn, then the light may adjust accordingly depending on where they need to see. There was one for an automatic steering and obstacle avoidance farming vehicle that would be used for people in agriculture. And there was one where a group of students made a robotic turret that would use a paintball gun and track objects using motion detectors, light sensors, microcontrollers, and much more, in which data was collected by the computer to test for accuracy, response time, distance, and so on. This is a good example because the team had to model the axis of rotation, the inertia of the device, and the torque required to rotate at a certain speed. They had to worry about the stability, the stress, the motors that turn the turret, and more. That's on the mechanical engineering aspect. An electrical or computer engineer would not be as knowledgeable in this regard. But then they had to worry about the microcontroller, the sensors, collecting the signals and data, using the computer for image processing and running the aiming algorithm, and much more. And this is what an electrical or computer engineer could work on as well, but the mechatronics students do it all because they're exposed to all these different fields. Now let's move on to HVAC. HVAC stands for heating, ventilation, and air conditioning, and also not included in the acronym is refrigeration, which is sometimes a part of it. HVAC engineers play an important part in various structures like hotels, apartment buildings, homes, large office buildings, and more. It's really about providing environmental comfort. Think of the heating system for your house. There's likely a furnace, which is where heat is created that warms the air. Then a fan is turned on that pushes that warm air throughout the ducts in the house to the vents to warm the house. Now this picture here shows central heating because the heat for the entire house comes from one point or central location. Also in a house, most rooms are heated simultaneously as there may be just one thermostat. But in a large building, things change because the amount of people or equipment in a room might demand more or less heating and cooling, and much more has to be accounted for. When you include the heating system, the air conditioner, the air filters, fans, ducts, and more, that's known as the HVAC system. The HVAC engineer has to account for all of this. So in a large building, there might be a centralized system for everything, or maybe for a few floors or whatever. But what if you want one room or floor heated or cooled differently than another with just that one centralized heating system? Well, the air will be heated or cooled appropriately, then some type of fan pushes that air through the ducts throughout the building to various rooms, just like for your house, but then everything will be heated or cooled at the same rate. So what you can do is use different dampers that control how much air gets into certain parts of the building by closing that flap a certain amount, which can be automated or manual. Then the air that gets through can enter the rooms through different devices like a register or diffuser. Air that exits a diffuser is distributed evenly and allows for slower velocity air in the room and raises static pressure. A register has adjustable blades itself that can control how much air gets through. So there are desirable air patterns that can be achieved with these different devices depending on what you want to do. You have to really consider where the air goes once it enters the room. But we're still not done, because once it enters the room, it also has to leave back through the ducts as well and circulate throughout the building. But the constantly circulating air throughout these ducts and rooms needs to be filtered and removed of things like dust or harmful substances by placing filters at different locations throughout the cycle. This is the ventilation part of HVAC. Some air will need to be exhausted to the outside environment as well and replaced with fresh air to keep everyone safe and as comfortable as possible. The HVAC engineers could design the network of ducts, the heating and cooling system, the filters, and more on the computer, which is something you'll see a lot like with AutoCAD. Then those are sent off to be manufactured, which the mechanical engineer could work on as well. Then they need to be installed in the building itself. Basically, the whole point of this was to show you just how complex the HVAC system can get. HVAC incorporates thermodynamics, fluid mechanics, and heat transfer, which are the prerequisite courses for the HVAC electives that you'll take. Now moving on to senior projects, there was one group of mechanical engineers who designed the HVAC system for a zero energy house, or a house that produces as much renewable energy as it consumes, which was also a project that a lot of engineers worked on. They had to decide what kind of heating system to use, like a furnace or a heat pump. They had to figure out how the ventilation would occur and how much cooling would be needed for the house based on size, location, etc. One team made a device that would take filter samples from an HVAC system within a subway so that they could monitor the content of air that's taken in. And another project was to build a cooling system for a data center room where large servers are kept and need to be maintained within a certain temperature range so that they don't overheat. Now on to the manufacturing concentration. This is about the process, machines, and tools that are used to turn raw materials into goods and products in the most efficient and economic way. Manufacturing applies to nearly every product you know of, like when machines assemble cars and their components, or when they're used for food production, or to assemble our electronics. Jobs will differ, but as a simple example, a mechanical engineer or an aerospace engineer might design the structure of an airplane wing and model the aerodynamics, the stress, fluid flow, and so on the computer before it's ever built. Then when that's all made on the computer, it's given to the manufacturing engineers who have to make it come to life and design the processes and incorporate the right equipment that will build the structure itself as efficiently and as accurately as possible. and all companies want to improve upon this process. In this concentration, you might even take classes listed as manufacturing engineering classes rather than mechanical engineering, but schools will differ. You'll learn the basics of manufacturing processes like casting or pouring hot molten metal into a certain mold so that it can then solidify into the proper shape, or different machining methods such as milling shown here, and more. Or you can take classes on electronics manufacturing and the fabrication of electronic products, printed circuit board assembly, and how these are actually made. Now lastly, let me just emphasize that manufacturing engineers are not the operators. They are not the ones that work directly with the machines to assemble the parts, which isn't to say that they couldn't take part in this though. But the manufacturing engineer is different. They take the engineering drawings or design and create the process for how it will be developed on the floor using various machines. One engineer made a comparison that it's like making the Lego instructions rather than building the Legos yourself, but obviously much more complex. They can work floor support where if the operators are having trouble or a machine breaks, they go to the manufacturing engineer for help. They also tell the machines what to do. Now this picture here shows a person operating the machine, but so much is automated and you need to input certain coordinates maybe and tell the machine to take actions at various points like putting on a car door, a wheel, sealing a package, etc. Then they also try to improve the process and make it better, like getting new equipment and testing that it works and will increase the company's profit at the same time. Industrial engineers, manufacturing engineers, and even mechanical engineers are common examples of people you could see working in a career like this. Now I talked about a senior project in our industrial engineering video about a team that looked at the process of manufacturing buses that could apply to this, so if you want to check that out, go to that video. Otherwise, in the next video, I'm going to go over the other subfields, which I'm going to group together to keep the video a little shorter, and I'll see you there. In this video, I'm going to move on to other subfields that aren't as well defined just depending on the university. So the way I categorize these may not be exactly recognized by your university, because like I said, some schools may call everything you see in this video just the general concentration, and you can pick what you want. But just get an idea for what interests you the most. First, I'm going to talk about classes and senior projects focusing on mechanics and structures or structural analysis, and I'm just going to call these all one concentration. These are about analyzing the forces on objects and structures, why structures fail, how to optimize the structure of something, and so on. There are a lot of these you can take because of how complicated certain structures or systems can be in terms of how forces, torque, stress, and more are applied and spread throughout whatever you are analyzing. Topics in various classes could be like learning elasticity or an object's ability to return to its normal shape after being deformed, or you could see more advanced vibrations classes to analyze complex vibrating systems. Honestly, most of these systems I've shown are analyzed by all mechanical engineers in required courses, but you can dive way further into them in electives. Staying on this topic, you may have classes offered such as biomechanics, which is applying statics, dynamics, and many of those physics concepts of structures to the human body or artificial limbs, and how forces act throughout those specifically. Again, these are kind of grouped together, but in the real world, these engineers could design the structure of an air or spacecraft. They could do testing to ensure that a satellite within a spacecraft can withstand the mechanical vibrations that occur. They can help design the structure of buildings to make sure they can withstand earthquakes or high winds, which is also something civil engineers would do. They could design the structure of a vehicle for safety in the event of an accident, or to be aerodynamic for better fuel efficiency. Or they could look at the moving engine and other parts of the vehicle to analyze their structures to ensure they can withstand the high speeds that occur. Especially with moving parts or dynamic systems, mechanical engineers have to worry about fatigue and failure that might occur over time rather than immediately. When it comes to weaponry and defense, which is a huge field, the mechanical engineers who work on them need extensive knowledge of structures. There's boats, submarines, and even elevators that mechanical engineers could help design. Moving on to senior projects, one team built a suspension that goes on a solar-powered car. This project required lots of engineers, as most big projects do, and one team of mechanical engineers made the suspension. As with all car suspensions, they had to ensure the suspension could efficiently absorb the energy from bumps, and during accelerating and stopping when the car dips forward or back a little, the suspension needs to help maximize the car's contact with the road. The suspension also needs to transfer the weight of the vehicle during cornering and much more. One team worked on the rotor structure of a human-powered helicopter. In 1980, the Sikorsky Prize was introduced, which would give $250,000 for anyone who could create a human-powered helicopter. No motors or anything like that. That was finally won a few years ago, which is not the senior project I'm talking about, but maybe you've seen videos for it where someone just had to start pedaling on a bike connected to lots of wires and huge rotors, in which he was suspended over 3 meters in the air for about 1 minute, which all met the criteria for the prize. So this group of students I'm referring to, for their senior project, tried to think of their own unique design for the rotor specifically, where they had to go into detail on the structure of the rotor to ensure it could withstand all the forces it was subject to while providing the proper lift to the structure. They couldn't test the entire thing, but made progress on the rotor design, which would be passed off to future students. Another project was to design the landing gear of an unmanned aircraft in a sense and avoid UAV project to ensure the UAV wasn't damaged during landing while they were testing the system. And because I talked about biomedical applications, one group of students made a prosthetic hand for an ex-Navy SEAL. They had to determine the best material to use based on the weight, strength, etc. They had to make sure the hand could support a certain amount of force for each individual finger. And there's much more that goes into these because the goal is to bring the best quality of life to someone who has lost their limb. One group designed the schematic for a roller coaster that could be developed at Disneyland, where they had to worry about the accelerators, the weight of the riders, fatigue of the roller coaster over time, and much more. And lastly, one team made a new structure design for small satellites that would be launched into space. Now the next concentration I'm going to categorize as energy and power. There could be mechanical engineering classes on fossil fuels, nuclear power, fuel cells, and more. You could take some petroleum engineering related classes that teach about oil recovery, drilling, onshore and offshore fields, etc. You could see classes on wind energy engineering. Mechanical engineers could do aerodynamic analysis for different wind turbines to see which is most efficient in converting wind energy into mechanical energy. You could definitely see mechanical engineers in petroleum engineering jobs because of how much goes into getting oil from the earth and designing and manufacturing the machines, wells, and so on that makes it happen. You could see mechanical engineers working in a nuclear power plant. They could work on designing solar panels that track sunlight and work on sizing down the solar panel or improving efficiency. Moving on to senior projects, there was one that would test the differences between stationary solar panels and ones that track sunlight throughout the day to see how much power is created from each one. They designed both systems and had to do the sizing, implement the tracking system, etc. One team worked to make a solar-powered oil well site that could run off renewable energy, specifically solar energy, and send sensor data back to the company that owns the site. And another was to create a system that would extract energy from exercise bikes that could then be sent to the power grid. Now other classes you could take I will go through more quickly, including automotive classes like vehicle design and learning about braking, suspension, and handling characteristics. Or you could take a class on combustion engine design and analyzing various engine cycles and combustion processes, which applies to cars but also boats and aircrafts. You could take more advanced classes on top of your required ones, like advanced heat transfer and diving more into conduction, convection, and radiation. There's classes on finite element analysis, which I've said before is a computerized way to analyze how objects and complex systems will react to forces, vibrations, fluid flow, and much more. You could take some more advanced controls classes, such as a fluid power controls class that focuses on valves, pumps, and motors, which all take part in the transfer of fluids. Some extra senior projects that aren't as easily categorized that I came across include a shotgun recoil test system, where they test different bullet masses, gun masses, and determine the effect on the recoil of the gun. One was to create a water conservation device, which would minimize the amount of work needed to provide hot water to a shower. And one was to create a smart airbag deployment system to prevent injuries due to unnecessary airbag deployment. They considered the size of the driver and their position relative to the airbag in order to maximize safety. And I'm going to stop there. Don't worry about whether you should enter mechatronics or structures or alternative energy if you aren't even in college yet especially. Just try to see if this is a degree you would enjoy pursuing and if there's a specific sector you are more interested in. Best of luck to everyone, and if you like this video, don't forget to like and subscribe, and I'll see you all next time.